In this lecture, I will present the working principle of Class D amplification. We will discuss about the power efficiency and in the end, also a working circuit will be presented. The following lecture will also analyze the simulation of the circuit in order to gain a better understanding. The main point of Class D operation is improving the efficiency of the system. For this, we clearly have to change the circuit, but which is the target that we have in mind? We need to increase the power available at the output of the power circuit. But since the power circuits that we have seen till now, Class A and Class B, are mostly done with the active devices, the best way to increase the available power at the output is to decrease the power dissipation that we have on the active devices, the circuit then. The improved efficiency has a lot of beneficial effects. For example, we can use less expensive and cheaper power devices that are smaller, and because we can use a package that is less performing in terms of power dissipation. The best way to reduce the power dissipation that we have on the active devices is operating the active devices in those regions in which there is very small power dissipation. And which are these regions? One region is the off state. When the device is in the off state, there is no current flowing through the device, and the power dissipation is zero, because the power dissipation is the multiplication of the voltage by the current. Another region in which the power dissipation is relatively small is the full on state, when the device is in saturation or completely on. In this region, the maximum current flows through the device, but the voltage drop on the device, the saturation voltage, the on-state voltage drop, we will come on this later, is quite small. Hence, the power dissipation is not zero, but it's quite small because we have large current but very small voltage drop on the device. This is the Class D operation. In Class D operation, the way the device operates as a switch. It will be either on or off, open state or closed state. The device will be driven by pulses to switch it on or off, and will dissipate a power that is very much smaller than the power that is available at the output. Ideally, the power dissipation in the on and the off state is the following. In the off state, the power dissipated on the device is the maximum voltage, the supply voltage VCC, VDD, the bus voltage. There are many ways to name this highest voltage into the circuit, multiplied by the leakage current of the device. But since the leakage current is quite small, this is, let's say, negligible in most of the applications. In the on state, we will have the maximum current, the load current, the current that flows outside the device, multiplied by the on state voltage drop. This is not exactly the current that exits from the circuit, but it is related to it. The on state voltage drop on the device, the saturation voltage, is just a fraction of VCC. Hence, this power dissipation is quite small. There are phases in which the devices will switch from on to off and from off to on states. There will be a power dissipation related to these transitions that will depend on the power devices and on the time that is needed for this transition. In general, as a rule of thumb, we can say that the slower the transition, the higher will be the power dissipation. And these are the sources of power dissipation on the devices that we will study later. Very often you can increase the power that you can drive and handle with the given power device working in class D operation, because the limitation is often not the maximum static power that you dissipate, because the device is not working in a static condition. There will be a limitation on the dynamic power, but usually you have just a limitation and you are much more limited by the maximum current and voltage. We will come later on the limits of the limits on the working region of the power device when we will study the safe operating areas. Let's put some number and make an example. Imagine you have to design a circuit with 50 volts of supply voltage and you want an output current of 2 amps, hence 100 watts of power. In class A operation, we need to use a power device that needs to sustain 50 volts, is able to handle 2 amps, and can dissipate, in the worst case, statically 50 watts of power. Switching to class D operation, we can change the ratings for our device. Voltage and currents are the same, but the power dissipation can be much lower. Let's say that the on-state voltage drop is around 2 volts. The power dissipation in the on-state is just 2 amps multiplied 2 volts, and this is just 4 watts. This means that with a 10 watts device we can easily do the job, and this is clearly an advantage. We can see this in a graph, in analyzing the input-output characteristics of a typical device. This is a BJT, bipolar junction transistor. Imagine that your device has these characteristics, and because of the package, because of the area, because on the way it has been made, or the cooling that you have, you can dissipate a given amount of power, PD maximum. The regions on this graph that are constant power dissipation are hyperbolic curves, and this green line is the maximum power dissipation that you can handle on your device. This means that you can statically work only below this green line. If this is the load line of your device, the red line, you can see that there are regions in which you overcome the maximum power dissipation. You cannot work here. And if you operate in class A, you will probably start working here and the device will fail. In a class D operation, however, we will either work in the off-state here with zero current and maximum voltage, and this is below the maximum power dissipation point, or in the on-state with maximum current and very small voltage drop, and also this is below the green line. As you can see, you can work with the same device, work in class D operation without having any problems. However, it is also important to pay attention to the time required for the device to switch between on and off states. because the power dissipation we discussed before is the steady state power dissipation, when the device is not switching. But there is also a dynamic power dissipation connected to the phases in which the device will switch from the on state to the off state. We will name PDS the average static power dissipation, let's say in the on state, because we will assume that the off state power dissipation is negligible. And PDD with capital D and small lowercase d for dynamic is the power dissipation during the switching. During the switching, the power dissipation is not easily calculated because it will depend on the current and voltage waveforms during the switching. This will depend on the devices, this will depend on the circuit, however. But we can say, more or less, that during the switching, let's say we are moving from the on state when the current is large and the voltage is small to the off state with the large voltage and zero current, there will be a transition, let's say like this. Current will decrease and voltage will increase. During this phase, you can clearly see the power dissipation is larger than during the on state, and this is the graph in red of the power dissipation. There are these peaks that are connected to the transitions. The same more or less happens during the transition from the off state to the on state. From the mathematical point of view, we can define the power dissipation, static and dynamic power dissipation, as follows. The static power dissipation will be the voltage drop during the on state multiplied by the on state current, the maximum current, and this is the power dissipation in the on state, multiplied by the time that the device will stay in the on state, divided by the period of the switching waveform. This is the static power dissipation. For the dynamic power dissipation, we can define this dynamic power dissipation as the integral of the current multiplied by the voltage integrated along during the periods in which there is the switching, delta T1 and delta T2, divided by the period. The total power dissipation, PD, will be the sum of these two components, PDS and PDD. Now that the topic is clear, which is the final target of these Class D operated amplifiers, we can start studying a typical circuit. In a Class D amplifier, the information content of the signal cannot modify the amplitude of the pulses, because these are a constant amplitude. When the device will be on, will allow the maximum current to flow. When it is off, the current will be zero. So there is no possibility to modulate the signal. But what can be done is modulate the width of the pulses. Let's say if we want more current on the output, we can have long periods in which the device is in the on state, so long pulses in which the current is maximum, and short pulses in which the device is in the off state. In other words, we will need and use a pulse width modulation, PWM, to drive the device and to transfer this information to the output. The simplest way of obtaining a pulse width modulation is obtained using a signal comparator to compare the analog signal that we want to amplify to a triangular waveform, as shown below. This is the input signal, and this is a triangular waveform with a quite high frequency. The comparison between these two waveforms will result in a number of pulses. When the input signal is larger, the positive pulses will be bigger, will be longer, and when the input signal is smaller, the output pulses will be shorter, hence the average value will be smaller. Here you can see the result, the simulated result. Imagine that you have an input signal that is this blue. Imagine that you have this signal that is this blue curve here, and in this case it is a sinusoid, and you compare this with the green line that is the triangular waveform that drives the comparator. The output pulses are in red. As you can see, when the input signal is larger than the comparison waveform, the output is high. And the opposite happens when the input signal is smaller than the comparison triangular waveform. You can also see that when the input signal is large in this first phase of the sinusoid, the pulses are quite long and there are very short zero pulses here. The opposite happens when the input signal becomes smaller in the second half of the sinusoid. The average of this pulse width modulated signal in red will be similar to the sinusoidal input signal. We will name the signal as f-sig for signal, and fm will be the modulating waveform, the triangular waveform. From a circuital point of view, we can design a very basic class D amplifier as follows. Here we have on the top we have the input signal, that is a sinusoid in this case, and here we have the triangular waveform. This X1 block is the comparator. This is the driver. This will generate the pulses that drive the actual class D amplifier. The class D amplifier is shown here in the middle with the green oval. It is very simple. There are just two power devices. The power device that will take care of pulling up this D output voltage, and it is connected to VCC, and another power device, a MOSFET, that is connected to the negative supply voltage that will drive this DC output voltage to VEE, that will probably be a negative voltage. These are two N MOSFETs, and their behavior is the following. One is on when the other one is off, and vice versa. As a consequence, on the D output we will have a number of pulses, long and short pulses. These pulses, however, are not the signal that we want. We need a kind of filtering to extract the average to get the original signal content. And this is done with this output filter. We will have an inductor. This is a second order filter. There will be an inductor, a capacitor, and this resistance here is the load. The previous circuital example shows us more or less which is the common process chain for a class D power circuit, power block. There will be a power supply, obviously, and not regulated one. The class D amplifier circuit, and a driver section that compares the signal the input signal represented here with a particular frequency sinusoidal signal ends with the particular frequency, compares this signal with the frequency with the triangular waveform, that is the comparison waveform. This will have another given modulation frequency. The pulse width modulated signal here is then demodulated with a proper filtering, and the final signal, the amplified signal, is provided to the load. It is clear that this signal, the modulation signal block, will have to let unaltered the input signal, the frequencies up to the input signal frequency, and remove the carrier frequency, the modulation frequency. The filter can be done in various ways. However, if you use resistors, these will be dissipating blocks and will reduce the efficiency of the circuit. This means that only L and C components are used in this kind of filtering, because L and C components store energy but do not dissipate it and allow a better efficiency for the overall circuit. Assuming that L and C components of the filters are lossless, in real cases there will be some power dissipation. At least the inductance will have some series resistance. The power efficiency can be linked to the power losses of the semiconductor devices. The power efficiency can be then defined as eta, will be the ratio between the power given to the load and the power taken from the power supply. That can be written again as power taken from the source minus the power dissipated on the power devices divided PS. That is also 1 minus PD divided PS. This power dissipation then defined on the devices then defines the efficiency of the overall circuit. We have seen before that the power dissipation can be divided into two components, the static one, defined by this equation, and the dynamic one, the switching power dissipation, defined by this equation. In the future, we will use these two equations to evaluate the power efficiency of the most common switching power circuits. A note on the pulse width modulation and filtering, because we need to design the LC tank, that is the filtering section of the class D amplifier, in order to keep the signal and remove the modulation frequencies. Let us name F with F the filter cutoff frequency. It is then clear that since this is a low pass filtering circuit, the low frequency pass, the zero frequency, the DC component passes unaltered, because this will become at very low frequency. This is an open circuit, C is an open circuit, while L is a short circuit, hence the input goes directly to the output, while at very high frequencies this becomes an open circuit and this is a short circuit. This means that the input signal cannot pass to the output. And since there are two reactive components, this will be a second order filter that has after the cutoff frequency a decay in the transition band that goes with the slope of 40 decibels by octave. The filter, we are saying that the filter cutoff frequency must be much larger than the signal frequency and much smaller than the modulation frequency. These two relations also mean that the modulation frequency must be much larger than the typical frequencies of the signal. This relation is straightforward because we want a lot of pulses to define very finely the input signal, but also tells us that if we can switch the devices at a very high operating frequency, we can treat and work with signals that have higher frequency. This means that we want to have devices that switch very fast with low switching times. In this plot we see the typical response of the LC tank. This is a function of the output load, but this is not very important because in our design we will have the signal frequencies that will be below the very much below the cutoff frequency f with f here, and must pass more or less unaltered, and the modulation frequencies that must be very far away from the filter cutoff frequency and will be cut away from the filtering action. After these comments on how to design the circuit and how a Class D power amplifier works, we can now present a complete circuit simulation of a Class D power amplifier. This will be a switcher CAD, that is a PSpice equivalent simulator analysis of a push-pull power amplifier operating in Class D with a pulse width modulation with a voltage comparator and one LC filter at the output. This also has as power devices two complementary power MOSFETs. And this is the schematic of the circuit. We will have the input signal, these sinusoids, that we can see as a frequency of 5 kHz. This is the comparator waveform, input waveform, that is a triangular pulse. The period is 20 microseconds, that is much smaller than the period is 20 microseconds, that corresponds to a modulating frequency of 50 kHz, that is hence 10 times higher than the input signal frequency. The comparator provides the pulse width modulated signal that drives the two power devices. This is one NMOS and one PMOS power. We have one N MOSFET and one P MOSFET power devices. This will take care of transferring this input signal to the output, the pulse width modulated signal, and then we have the filter. From the values that are being set for L and C components, we can calculate that the cutoff frequency given by 1 divided twice pi multiplied the square root of the inductance multiplied by the capacitance is 7.9 kHz. Since the signal frequency is 5 kHz and the modulating signal is at 50 kHz, we can expect that this filter will work properly in our application, since the modulation frequency is much larger than the signal frequency and the cutoff frequency is between them. A note must be discussed on the LC filter. When we deal with analog amplifiers, amplifiers that have to provide an amplified analog signal to the output, dimensioning the output filter in this way is adequate. In the following, however, we will use different circuits whose primary purpose is providing a regulated voltage and power to the output. This means that the signal frequency is 0 or almost 0, and the design of the circuit is no more done using this cutoff frequency equation. The output circuit, the filtering circuit, will be no more a filtering circuit. We will have to think of it as an energy storage circuit. And the analysis that we will do will be slightly different, but this will be done in some of the following lectures. Video. We will conduct a simulation of the Class D amplifier that has been presented now in order to gain a better understanding of the working principle.